powinien działać.
Dobra.
Tak. To jest do rozdawania. Aha, on sprawdza ten.
To dziecko, które wiesz, nigdy to nie jest najgorsze, nigdy nie jest gorsze. Który myśli, że wszystko rozumie, mówi, jest pracowników, my jako członkowie lubimy pracowników, bo dużo robią dla nas. Także
Tak. Teraz.
tak. I ta druga to jest Margaret.
Margaret. Małgorzata.
Tak, i
Margaret.
ona jest albo czeszka, albo jej matka
Aha.
czeska, albo
Margaret. Już sobie zapiszę.
Margaret Ferris. I tyle. Wiesz, chodź poszukamy pola, bo tutaj nic się nie dzieje, już jest 7.
Tak? I jest godzina 7:00, dokładnie.
Dokładnie. I oni powinni wyjść. I najpierw musimy ustalić. Okej.
So, sequence for it, I'll introduce you. We got a bottle of water here. Okay. You guys can just have a seat here in the front. I'll make kind of welcome remarks and introduce you. Podium's there. You go for about 45 minutes or so. I'll be in the back of the room. If for whatever reason we're running long or something like that, I'll just be seated waiting. That's the time. And then the goal will be about 45 minutes, and then we'll take questions. So I'll come up with a microphone then, and we'll take questions from the audience. We'll pass them a microphone so that, because it is live streamed, that the questions go. Perfect. That's perfect. That's just fine. Sometimes we go long. And what questions? That really beat up flag there is that anymore. So, this one here, 1, 2, 3 is close. And right here is Volcans. Is it? Good evening. Welcome to the Explorers Club. My name is Paul Tangy. I am professor of military science at Fordham University, and I'm also vice chair of our public lectures committee here at the club. So on behalf of our chair, Natalie Cash, I'd like to welcome all of you to the Explorers Club for one of our oldest traditions here. Since 1922, the club has conducted public lectures in order to help us with our core mission of promoting the scientific exploration of land, sea, and air. So, by way of welcome, can you please raise your hand if this is your first time at the Explorers Club? That's awesome. So, look around. So first, welcome. You belong here by coming in here. Like, that's the community of the Explorers Club is special because of the people who show up here. If you raised your hand and you saw someone near you who doesn't have it on there, get to know them and ask some questions about the club. The way this is going to work for tonight, we're going to have a lecture for about 50 minutes or so, and then there'll be opportunity to ask questions at the end. And then we'll aim to wrap up around 8 o'clock, and then the bar will be open downstairs. You have to be a guest of a member to go in there. So again, you saw who didn't have their hands raised. Ask those people to bring you to the bar afterwards. All right. We are very lucky tonight to have an aviation-themed lecture. And I want to start by recognizing one of the club members who's here, Peter Nell. Peter, can you please raise your hand there? So Peter is preparing to do a solo circumnavigation of the world in an airplane. He's going to be doing the westbound route via the Aleutians in Japan, late July, which happens to be the 100th anniversary of the first circumnavigation of the world by the Douglas World Cruisers in 1924, which I'm proud to say was a U.S. Army Air Corps expedition. So Peter, good luck with that, and thank you for being here tonight. So again, afterwards, talk to Peter. But for the real show, and the reason why you guys are all here tonight is for the Perlan Project. And we're so grateful to have Roberta Vassadin here to discuss this project. In short, well, she's going to give you the details about it. But this project is aiming to have the world's highest wing-borne flight in a glider. So the edges of space, 90,000 feet is the goal, with 0 emissions. I first read about them about 2 years ago. I reached out to Ed Warnock, the founders or the CEO of the project, and said, would you be interested in coming? I do also want to say that not only is the Perlan Project amazing, but this schedule, tonight's lecture topic became available about 2 weeks ago, and I reached out to them and said, would you be willing to come up here on short notice and do this? And their answer was yes, and so they flew in. I think he started at 4:30 this morning, did you say? So thank you for the effort that you've made to come here tonight and share this special story with us. And so with that, please welcome Roberta from the Perlan Project.
Wow, it is an honor and a privilege. I can't tell you. It's just like my dream come true, honestly, to see all you people out here and in TV land, and oh, this is excellent. I'm speechless. I hope I can go on, but this is so cool. You know, I've started from the very beginning, a little girl always wanted to be an explorer. And so the Perlan Project and our involvement, my husband and I, Arnie, will be talking a little bit about what we've accomplished with the Perlan Project and where we're headed, and you guys can all be part of it too. So I'd like to carry you along tonight and show you what we can do.
Yeah, and so I want to introduce ourselves a little bit. We are AV Experts is the company that Roberta and I own and operate, and we do R&D flights. We have an aviation company that researches remote sensing equipment, radars, optical stuff, all different types of high altitude things that a lot of it are involved in the DoD, and it merged into atmospheric research and air sampling and stuff like that. And so, and then when the Perlan people approached us, we saw their record flight back in 1917, in 2017, excuse me, a little bit, but we happened to notice that, and we were operating some high altitude missions and went, wow, wouldn't that be great if we could use the egret, which is a very specialized airplane, to pull the glider. The gliders operate at very slow speeds, and so there's nothing that can really do it except the egret. And while we were thinking about this, the egret team reached out, or the Perlan team reached out to us, and we said, well, yeah, we're interested in this. This is a perfect fit. And so that's how it all got started. And it's just been a magical ride flying all of these missions. And I'm gonna let Roberta take over. She's gonna,
I'll give you a little bit more background on that. So the Perlan Project is a team of volunteers. We're all volunteers. We started in 2006 or so. You'll see the history. This is our last expedition down to southern Argentina. We are based out of El Calafate, Argentina. And this is our on-site crew. There's about 25 of us, give or take. And over the history of the project, we've had about 50 people involved. We have a three-pronged mission. We really take exploration very seriously, obviously. That's why we're here. But we really want to inspire people as well and show them that, you know, anyone could be involved in these kinds of things, especially the youth. That's one of our big pushes, is to introduce people to exploration. The other thing that we like to do is innovation. The airplanes that we operate are very unique. They were specially designed and built for this purpose, and we're looking at not only just making a record, but really understanding the atmosphere in which we're, you know, flying, and understanding the Earth through that atmosphere. The project all started out when Einar Ennevisson, he's the guy on the left here. Let's see if I can get the pointer. This guy. He is was a test pilot. He just recently passed away, unfortunately, with NASA, and he flew this plane called the Grob Strato 2C. It holds the record for a high altitude flight of about 65,000. And during the time that he was flying, he happened to be at the DLR, which is the equivalent of NASA in Germany. And he saw a picture on the wall, which is the picture you see on the left here. And there was these weird bands of color over the mountain, a mountain in Sweden. And he was like, whoa, what is that? Well, that's really cool. Could that be air moving over, these are altitudes of 75,000 or so. And so because he was a pilot, he always wanted to see what was out there. And he's a glider pilot, so his dream was, wow, I should take a glider and go up there and see if that really is there. Oops. So why is it called the Perlan Project? Well, the Perlan Project is named for the polar stratospheric clouds that look just absolutely stunning. This is an example there in the slide. It's iridescent, especially at night. It's so high, it's about 75,000 feet up, like it says on the slide, 50 to 80,000, but we see it, about 75, 80,000 feet. And it glows in the night sky because the sunlight, after the sun sets, there's still sun up there illuminating that. But despite its beauty, it really is deadly because nitric acid is incorporated into that cloud, and nitric acid interacts with chlorofluorocarbons that are down, they were released into the atmosphere a long time ago, and it actually catalyzes ozone and destroys it. So when we see those, it makes us even more inspired to try and figure out how we can understand the atmosphere more. Clouds are everywhere. Most of the clouds, of course, are in the troposphere, the lowest level of the atmosphere. This is a cloud called, what is it called? Do you guys know? Very good. It's a lenticular. Absolutely. Lenticular means a lens, and you can see why it's called that, because it looks like a lens, and this is a really dramatic one down in, yeah, El Calafate. And that, again, is in the troposphere. But the clouds that we're dealing with are up in the stratosphere. So how you get clouds and things to form, there's movement in the atmosphere of air currents. And as you see in the slide here, you have the lowest level of the atmosphere, which is the troposphere, and then you go up into the upper level above that, and that's the stratosphere, and that's where the Perlan flies, and then above that is the mesosphere, and it goes on and on. So what we're looking at is a wave that actually sets up because of atmospheric winds that go around the world. If you're at all familiar, as I'm sure you guys are, about geography, you have different bands of wind going east and west. So these are the westerlies that go along the southern part of South America, and then when you get further north, then you have easterlies. And so when you have the westerlies come into the Andes, which is a really high chain of mountains along the western border of South America, the wind is forced to go up and over. And that's nice. That's what causes those lenticular clouds. But down in the southernmost part of Argentina, let's see if I can point to it. This is the South Pole here, and this is South America, and right where my pointer is El Calafate, where we operate out of. But in the wintertime, we have the polar vortex, also known as the polar night jet. It's an atmospheric river zone of circulation, which is going from west to east. And once you know, that's that same wind pattern that we see on the earlier slide, going west to east, hitting the Andes. So what it does is when this interacts with the Andes at a high level versus the low level, it supercharges those wind currents, and it causes the waves that are in the troposphere to amplify. And that's what Einar saw, was the amplification of these huge waves. These are the biggest waves that we actually have in the world. So if we were to map some of them, you can see, again, the troposphere is on the bottom, and there's little squiggles. And then the tropopause, where there's a change of temperature. As you ascend in the troposphere, you get colder. In the tropopause, it changes, and as you ascend in the stratosphere, it gets warmer at the very top because of the ozone destruction. Anyway, the bands of color are the bands of up and down air. And you can see as you go higher and higher, the intensity gets stronger and stronger, and that's because the air is moving in a wave, a gravity wave. So here we are, 2006. Einar got Steve Fawcett to go and fund this expedition. Steve Fawcett, I just learned because I saw a picture of him on the wall, he is one of the explorers. So this is really cool. It's coming home to me, see? And they started and they said, oh, we should go down to New Zealand or should go down to Argentina and try and find a way that we can get into this wave. So they had a standard glider, and because they knew they were going to try and set an altitude record above 49,000 feet, they needed pressure suits. So they got NASA to help them out. Einar was a NASA test pilot, so he got his test pilot suits, and they went into that glider, and it was successful, except it was very uncomfortable. Because of the pressurization issues up there, the suit blew up. They couldn't move. They were like, you know, awful. And their feet froze to death. It was very cold. So at that time, as they were descending, they said, we have to do better. We got to start the Perlan 2. So that's what we're flying today, is the Perlan 2. The Perlan 2 is a specially designed airplane that is designed to go and fly at up to 90,000 feet. There, at 90,000 feet, you only have about 2% of the air density that you have at sea level, and 98% of the gravity So it's a very extreme, harsh conditions. The temperatures there are down to minus 70 degrees Celsius, which is minus 100 if you're a Fahrenheit person. And the airplane was specially designed to take those types of atmospheric and extreme conditions into thinking. So because it's a glider, it has to be light, and it has to be strong, especially with the pressurization issues. And so we made it out of all carbon composite construction, and it's a sealed cabin. And you'll see as we talk about pressurization, we did it very simply because we have no electricity in this airplane. So we do it with a scuba tank. It's very innovative. So we pressurize this space capsule basically with wings. And there is a picture of how the layup was looking when we first started making it. Greg Cole was the designer. This is, again, a very unique airplane, one-off. The final assembly was in Redmond, Oregon. It looks like Spaceship One, you know, and the reason it does is because it's the same reason. You want the littlest portals that you can, and you want the hatches on the top of the airplane here to be plugged doors so that the pressurization pushes up against them and seals that. When they made the airplane, they want to make sure that before they put a human being or two in it, that it was safe. So they went through a whole series of ground tests and vibration, flutter, computational fluid dynamics and things to make sure that we were safe with the people. And we designed it so that it would fly best, knowing that we wanted to go to 90,000 feet potentially, and you have to get up there. We made it so that it was okay at 60,000 feet. That's where it's optimally flight tested. As you may or may not know, airplanes have a stall speed. It's the speed which, if the air doesn't keep flowing over the wing, the airplane will literally drop out of the air. So the stall speed for the airplane, as you go up in airspeed, in altitude, it changes. Because the air is getting thinner, you have less molecules of air going over the wing, so you have to fly faster in order to stay aloft. So you can see it was 200 knots at 90,000 feet, whereas down here it's 47 or 40 for the stall speed. Right, exactly. And so the never exceed limitation, so you don't pull your wings off, is another number that we're very interested in. And so as you go up, you can see the actual speed that you're flying versus the perceived speed that the pilot sees on his gauges in the cockpit. And so the stall speed at 90,000 feet is 40 knots, indicated airspeed, and the never exceed speed is 54 knots. You can see how very tight those are to each other. That's what an aviation engineer would call the coffin corner. It's when you will fall out of the air, even if you're flying. It's deadly if you get there. But we have a lot of very dedicated people. These are the pilots that are part of this project. There's 4 Perlan pilots. The lead pilot is Jim Payne. He's the guy that's right here. Miguel Inarmendi is another of the pilots. This is Morgan Sandercock. He was one of the people that actually put money into this. And Tim Gardner, he's also, he was on the record-setting flight for our highest flight with Jim when we did the highest flight in 2018. Arnie, you've met him. He's the guy that is my husband. He's the egret pilot. And there's only 1 seat in that airplane. Otherwise, there'd probably be more people that go up in that. But he'll tell you more about that airplane. I'll talk about the Perlan, just the environmental parts, just a little bit more. Because we have the need to keep pilots alive, we need to have life support systems on board. And there's 2 basic types of air that we talk about when we talk about the Perlan. Air in the cabin that's used for pressurization, and oxygen that's used to keep the pilots alive. The cabin air is, by design, less than 30% oxygen. And we want it that way because we learned from the problems with Apollo 1, when there was too much oxygen, we could have spontaneous combustion. We don't want that, especially up there. So we developed a special, using a firefighters' rebreathing apparatus. We repurposed it to put into the Perlan so that it could be the thing that we use for keeping the pilots alive. This is the rebreather here. He's breathing 99% oxygen, and it's all contained so that it doesn't get out into the cabin. The cabin, though, is pressurized by a scuba tank, like I mentioned before, and so that's only 21% oxygen being underneath that 30% oxygen. And it's dehumidified, because if there's any humidity that goes into that air at that temperature, when it's minus 70, it just freezes immediately onto those windows and you can't see out. So those little round windows, which you need to see out of to be able to land and maneuver the airplane, just can't do it. So there's been a whole lot of innovation on that side too, just trying to bring in like tear-off panels on the windows and things. So in the event that we ever have an emergency, we want to make sure that the lives of our pilots is good. So we have some systems for that. If we had a loss of control at high altitudes, we have a drogue chute that would come out. And if we really needed it, we can explode a parachute out and out of the back of the tail of the airplane. It's a full BRS parachute that's manually deployable. So these are, of course, not without risk, these flights, but we have a very concerted effort to discipline ourselves so that we are not getting anxious and going above the values that we set out on our test cards. We have a whole discipline team of test engineers that watch what happens, and we've actually built test equipment into the airplane, in the wings themselves. So one of the things that we do is we do a flutter excitation, which is used to make the airplane's wings slightly vibrate. And as we go up every 5,000 feet, we do that so that we can see if there's any negative effects that as we get closer to the coffin corner and we get closer to that stall speed, we don't want to drop out of the air. So we do asymmetrical and symmetrical flutter, and it's telemetered down to the ground, and in about 10 minutes later, the people on the ground can go back and look and say, okay, yes, you're clear to the next 5,000 feet. So we've made our way all the way up to 76,000 feet now, and we're ready to go to the highest point. We've done our last test point for that. And this is the flight test envelope that we've achieved, and we're ready to make it to the top now. We're just waiting on the weather. Arnie, you want to talk about a little bit about the operations that we go through here?
Sure. Well, as you know, we operate down in El Calafate, which is the southern tip of Argentina, due to the weather conditions and everything. And so getting this whole operation down there is a logistical nightmare. The glider is all packed up in the equipment into a 40-foot container, and it is shipped from Minden to San Diego, and then takes on a ship and goes all the way down the coast to Panama and around, and that takes several months to accomplish. And then the egret, we get it ready out of Dallas, and it takes me about 6 to 7 stops to get down there. I usually take off from Dallas and go down into Mexico for a fuel stop, and we'll stop in Puerto Rico, spend the night there, and then go on into Ecuador or northern Peru, and down into northern Chile, stopping along the way, and then into Mendoza, turning the corner. That is flying along the backbone of the mountains the whole way in the Anaconda Desert and stuff. So you see, I get to see volcanoes going off, and it's just an incredible trip to get to see. And then when you finally turn the corner about to go to Mendoza, then you get the downwind leg where you get the huge, huge winds going across the mountains there. And I land there and spend several days clearing customs. That's another thing, getting all of this stuff through and everybody. But luckily, the Argentinian government and people have been very supported. We've been now invited, so the support from Argentina is just incredible, and that smooths it along. And from there, then I fly down another 1,000 miles or 1,100 miles down to El Calafate, where we do the operations. And so once all of that stuff gets together, then we get to fly. And flying the egret, to pull, the egret is one of the only airplanes that can pull a glider because it can fly slow enough and high enough to do this. And so it normally takes off at about 95 knots. That's my normal speed, but we like to rotate with the glider at about 75 and climb out at 80 knots. And so with its powerful engine, I don't know if we've got another slide. That's the way it started in the early days with Steve Fawcett. We had a little piston engine that's normal for glider type towing. The problem was in El Calafate, to get to those mountains out there in that little piston airplane, it climbs so slow, and you end up getting in the rotors of the mountain waves that come out, and so you can get into severe turbulence. It doesn't climb fast enough, so if there was a problem, the glider can't get back to the airport. And so there was a lot of logistical problems with the small airplane, and thus comes the egret into the fray. And we can take off out of there. That's Lake Argentina. You can see there's a big iceberg right there. And if you go up around, up around the lake up here, the ice fields are all back in there. The glaciers galore. And the local people have been generous enough to take us out in boats and get to go up to the ice fields, and it's really fun. But the purpose is to get it up, and so the egret can pull the Perlan glider up through the troposphere, which everybody knows it. And the whole purpose of the mission is to check out the stratosphere. So we can get up into the stratosphere every single flight. In the previous 20 years, they only got up there like, I think maybe one time. And the glider's limitations with oxygen and batteries and all of that kind of stuff, the record flight was 6 or almost 6 hours of flying. And so you don't have the daylight, and you don't have the ability to do it with the underpowered airplane. So that's where the egret comes in, to where we can get them up in about an hour and 10 minutes to 45,000 feet, and let them go explore where we want to be. And that's a good picture of the egret. The mountains, the Patagonia mountains are just so incredibly beautiful. Operations down there are quite challenging. There's not a hangar big enough for us, so we've had to manufacture coverings and electrical heaters and start carts, and it just goes on and on. We didn't have propeller covers, so they're covered in plastic bags in the meantime, garbage bags. And that's the egret crew there that takes care of it with the flags on the side of the countries that we've gone through on the way down and back. There's a picture of the cockpit flying around. It looks like it's on the route down from Mendoza, which will go into the next deal where we're talking about the mountain waves and the turbulence and everything. On the trip from Mendoza down to El Calafate, I run into waves across the mountain that are just incredible. I'll be flying along at about 40,000 feet, somewhere in that neighborhood for the cross-country flights, doing a normal flight, and then all of a sudden the airspeed starts just going down. You're trying to maintain the altitude, and it goes from cruise speed of about 140 indicated, 130 indicated airspeed, and it starts going down and down and down and down until all of a sudden you're down to about 80 knots, and I don't want to go any slower than that. So then you got to sacrifice altitude. So then now I'm holding 80 knots and going down and down and down and down. The last time we went, we lost 3,000 feet before I finally flew out of it. And Roberta will talk more about the mapping of these waves. And the next time we go down, I'm hoping that we can use the same technology to map this waves to where I can look at it and plan the flight to move over to the left or move over to the right. You can't just do it randomly. You have to be able, with air traffic control and everything, to do it and then ride the up wave. Because after I flew out of that down wave, the same thing. All of a sudden, it's pushing you up at that speed. You get back up to altitude, and you're pulling the throttle back because you're going to overspeed. You're going to go exceed your Mach number, and you go back and back and back and back until you're at idle. And so you go in and out of these waves, and the 3 times that I've flown down there, it's happened almost identically each time. So that's something that we're going to carry on. And here's where usually when we get up into the stratosphere, the egret will start making contrails, and that's why Jim would always say, you know, it's the only glider pilots that I've ever seen their tow plane make contrails. Also, we use a rope called it's about a 300-foot rope, Dyneema, I believe it is. It's a really, really thin rope. And at times when we started out, it can ice up in that contrail, and we get ice crystals that actually have gone back and hit the airplane, and we were kind of wondering what was that. So some more things. That was that's the world record flight. You can see where the oops, if I can get the thing back there. At any rate, we climbed up and did the release. You know, with the highest altitude release we did was 47,600 feet. And then, I don't think that was there, but this one shows where they went up and did the tests and continued on up to over 76,000 feet, where the glider beat the U-2's altitude record and became the highest subsonic flying airplane. The wing, you know, we're talking about winged airplanes and not ballistic flights, you know, where you go supersonic and they go on up and stuff, and then they just mush down around the other side. But this is an actual winged flight. So it's very, very exciting. And I think this is a short video, right? If you just press it once again.
Jim says it's like flying in a homesick angel. I mean, look at that climb angle. It's just incredible. Here we are making a contrail. Oops. This is Jim Payne. He sits in the front cockpit of the Perlan. He just released from the egret. You'll see this from our tail camera now. This is very choreographed. Each airplane knows where they're going to be at the right time. So you can see how limited, there's very little room inside that cockpit. Very claustrophobic. Here's they're doing the flutter tests and putting out the spoilers, the stalls. They're on their way up to 76,000 feet. Up there, you can see the curvature of the Earth. The atmosphere turns dark. We never saw the stars yet, but I'm hopeful that when we get to 90,000 feet, we'll be able to see back cockpit is the person that does a lot of the engineering tests. If you listen, he's putting the pressurization in. He's making sure that that's from that scuba tank that I was telling you about. And we come back and land. People go, how do you get back from there? Well, we're an airplane, so we can land. So you can see the size of the airplane with respect to the people. So it's very cool. It's very inspiring. So we always are into safety. So we have a whole fleet of people that are looking after our pilots and our staff. We have a capsule communication center, just like a spacecraft, you know, a Capcom, and they have a digital readout of all the systems that are in the Perlan, and they're making sure that they're all in the green. If there's ever anything turning yellow or red, we make sure that we understand why that is, if the missions should continue or not go on anymore. We're always tracing where the plane is at all times, because if there was any problem, we want to know where to go to get it. And these are very inhospitable areas, as you can see from the pictures that we showed. This is the southern Patagonia ice field, so you might land right in the glacier, and the only way to get to you is by helicopter at that point. But fortunately, the local authorities there are very proud to be able to serve with us. So it's a great teamwork and partnership that we have with the Argentinians. For the public, we've developed a virtual cockpit, so you can follow us from wherever you are in the world. We encourage you, all of you, to join us on all of our missions. You'll see at any time that we're flying, you'll get a ping on your email or on your phone, and you can watch our flights, you can trace us with it, and we even have we have live stream video now with either the cockpit or the tail cameras, and even inside the Capcom. Like I mentioned, we're not just looking for setting records. We are also a scientific exploration. And we do collect different things on our expedition. Of course, we're trying to map these waves, these huge waves of air currents, because if we can model that correctly, then we can drive the global climate change models and the weather climatological models that are used to predict the weather. There's very few weather stations or any type of research stations down that look at the atmosphere in the southern hemisphere. So when we are down there, we are doing actual, real, live science. We also have different types of sensors on board. We measure the temperature, we look for radiation, ozone, particle and dust distributions, and we also have the CubeSats. CubeSats are little mini experiments. They're 10 centimeter on a side. They look like you see on the side here. This is my daughter, actually. She was in El Calafate. She's the youngest member of the Perlan Project. She's been serving since she's been 12 years old. She is now 18 and ready to graduate from high school. And she was the one that started trying to put all the different sensors and the CubeSats. We were fortunate this year. We work with the Teachers in Space, which we have Liz here, the president of the Teachers in Space. I never got to meet her until now. I've seen her picture, and it's just really cool because we encourage young people of all ages, from little kindergartners all the way to college and career people, to create these CubeSats that are scientific instruments and things where they can get involved and inspired to do science. One of our favorite projects, one of the first that we ever ran in the Perlan, was the marshmallow in space. That's what you see here on the left. There was strain gauges put around marshmallows, and as the payload ascended, we wondered if the air inside a marshmallow would expand. And then if it did, with the marshmallow, then when it got back down to Earth, would it collapse back again or not? What do you guys think would happen? It did, but not all the way. That's right. And so this was set up by a museum in Oregon, and these were kindergarten kids, 5-year-olds. So we're trying to inspire the youth. This year, we actually also made a bay for the CubeSats in our egrets. So any of the CubeSats that didn't fly on the Perlan, which it only holds 3, could also fly in the egret as the counter. And also with the in the bay here that I'm underneath, this is where the CubeSats are. But there is also this bay here that can hold CubeSats, and this device there is called a Talus Link. It's basically the world's highest hotspot. We use it to do in-flight video and recording and beam down scientific data to the ground. One of the other things that we do, because we are a meteorological station, is we launch weather balloons before and after and during each of our missions to try and, again, get a feeling before we go up or during that mission, what is happening in the atmosphere. And here is a weather balloon launch that you see. I think we've been doing this since 2006, and in the last couple of years, since we were working with the egret, we've set 4 world records. And we're very proud of that. And like I said, the next record, we're hoping that we can get above the SR-71's record, which is 85,000 feet. The third prong of our mission, of course, is inspiration. And we really like to inspire all the people, not just, older people or young people, but everyone. And so here's some of our outreach efforts that we've been doing. And we have a group of people, young people that have served as interns with us. And it's amazing because every one of them have gone on to stay in aerospace and do something with us. We've gotten a lot of recognition for our efforts, which we're proud of. We've gotten between 14 and now I think up to 20 prestigious awards and world records. And we've been highlighted in many different publications and all over the world. And it's just great that people get inspired by us. I still can't get over it. Now, one of the things that we're looking for is, what do we do in the future once, how do we transition this kind of technology to helping people? Well, one of the ways is through aviation safety, avoiding those turbulent, even tropospheric waves. So as you see, severe turbulence is really a big thing. And then Perlan is pioneering a way to visualize the waves. And that's what Arnie was talking about earlier, where we could actually, where the red and the blue is, that's the up and down air. If we could stay in that up air or avoid it at certain times, we can fly more safely. We're also looking at the weather and climate. Like I mentioned, we're trying to drive and seed the models that we use for the global circulation models and explore that wave, the Perlan cloud. What is that Perlan cloud doing? How is it interacting really with that ozone? And more atmospheric physics type things. When we were down in 2019, I think it was, yeah, we were there and our flights were cut short dramatically because all of a sudden the stratosphere started warming up. We can only fly when it's cold because when it's cold is when that polar night jet is doing its regular circulation and hitting the Andes Mountains. And then all of a sudden it just stopped. And we took a flight and the atmosphere, the temperatures were just crazy hot. And so you can see what it should have been and what it actually was. It was incredible. It was a sudden stratospheric warming, they called it. It is common in the northern hemisphere, but it's extremely uncommon in the southern hemisphere. There's only been 2 incidences of that, and we were there for 1. And so here we were with actual scientific measurements, and us, the atmospheric scientists, were very excited to be able to share our results with the rest of the world. We're also trying to be more green. Obviously, you know, we're trying to understand if fossil fuels are contributing in a negative way to our atmosphere. And being a green, non-emitting type of airplane, we have the ability to then look to see what the atmosphere is like. And because we're a glider, that can actually just, in effect, hover at 70,000, 60,000 feet. We can get a very good feeling instead of, you know, having to shoot through it. We can stay in that atmospheric wave and really sample the air zones there. We're working with the Thales group, which is the same people that put in that box for the world's highest hotspot, but they're also doing AI for us, so they can try and predict where should we go to fly to get into the wave, the uplift. If we could do that predictably, we could actually save millions of gallons of fuel if, like, an airliner would to do that and ride those waves. Also, the Perlan Project, because it's a uniquely designed airplane, we're also into designing other types of maybe follow-on missions. And one of the big things is as you go higher and you get to a higher Mach number, you have to watch out for the temperatures of your air. And we saw through the Perlan Project that there's very dramatic and short distanced changes in the temperatures, which was never even thought that could occur. And we're like, if we had to do the flights up at 90,000 feet or even 70,000 feet, if we were to put a commercial airliner up there, they have these engines controlled dynamically with a computer system called a FADAC, and that engine would have to change its combustion ratios in a quicker, dynamic way than they are currently doing. So just being aware of the problem makes the engineers that design airplanes, gives them a food for thought. The other thing, the Perlan Project, when we fly that high, we're actually simulating the atmosphere that you'd find on Mars. So in effect, we could be predicting different types of airplanes that maybe we could use on the Mars surface. It's very extreme, very cold, very low atmospheric densities. And these kinds of thoughts are the things that really inspire people to think further. So what are we going to do in the future? Well, we've formed, at least for the meantime, when we're not flying, we've put together the Partners Project, which is the Perlan Atmospheric Research Team. It's composed of 4 different companies and organizations: the Perlan Project, Weather Extreme, which drives our weather modeling, AvExperts, which is us, the eager tow plane, and Stratodynamics, which is a balloon-launched payload. And we're trying to explore the atmosphere a little bit more. We've also been working with Airbus on their Blue Condor project, which is putting together a hydrogen engine-powered glider to understand if hydrogen is a fuel that's viable for powering an airplane. The reason that we're concerned about that is because water vapor, which is the emitted thing after you burn hydrogen, is one of the world's biggest greenhouse gases. Water is very, it'll keep all the heat in. And so if we have emitted a lot of water vapor into the upper stratosphere, and the water droplets are so small that they stay up there forever, we could actually be doing more damage. So we're doing a lot of research along with Airbus to try and understand that a little bit better. So what's next for us? Well, we've gotten higher than the commercial airlines, and we've gotten higher than the U-2. Like I said, that SR-71 record is the thing, the low fruit that's hanging ready for us, and we'd like to try and achieve that too. So that's what the next thing is, and I'll give you a final slideshow briefing here, just to get a feeling, again, for what the people are and how the team is organized.
The 10 flights that have been above 50,000 feet that have been done by the Perlan Project represent success.
We've taken the previous record before the Perlan Project, 49,000 feet, and we've kicked that up to 76,000 feet. So we've made that record unreachable for anyone that's not really serious.
The Perlan Project is a fantastic voyage to the edge of space, riding stratospheric mountain waves. Waves in the stratosphere are generated when wind blows over a mountain range and creates waves, and then the polar vortex transmits those to the top of the atmosphere. The Airbus Perlan Mission 2 is made up of all volunteers.
Everybody on the team is really putting in effort beyond 100%.
The team over here is comprising of many people coming from different backgrounds, and all of them are very highly trained personals, and they bring their expertise into the team.
Personal goals, to find out what's up there, to find out where the conditions really exist at 80, 90,000 feet, in that layer of the atmosphere where no other airplane can fly.
And the dynamic is that we're held together by a common vision. Einar Enevoldsen observed stratospheric waves and dreamed that they could be soared to the edge of space, and to be able to accomplish Einar's vision is more important than records we've set. The altitudes with which we've flown approximate the conditions found on Mars. The air is so thin that previously it took giant motors to drive airplanes. We're trying to demonstrate that it can be done with less energy and zero pollution. For the last 10 years, we could not have done this without Airbus. They have been the best partner that we possibly could have imagined.
We're doing the impossible right now. And how often nowadays do people do the impossible?
To be able to actually get it into the stratosphere and to have a number of flights up over 60,000 feet. We've gone where no other glider has ever gone, on flights that people told us was outright impossible to do.
We're carrying about 20 experiments. Half of them have been built by students. The students that have built CubeSats are going to be able to receive data that is taken at the edge of space. They will be able to follow us real time, and we're hoping that doing real science real time will charge their imaginations and inspire them.
I was inspired to take up Soaring because of a National Geographic article. And hopefully the Perlan Project has inspired other people to take up flying, engineering, and math.
To me, one of the things I said to myself coming into the Perlan Project is I want kids to be inspired by this, and every gliding club around the world should get one more member. Many, many aviation textbooks in the future will have a chapter on high altitude, and Perlan's going to be front and center in that.
For Airbus Perlan Mission 2, it has been an amazing journey. It will continue to be amazing. So stay tuned. Let's see what the future holds.
Jackie said it. So I really appreciate your time and the opportunity, all of us in the Perlan Project, all of us engineers, international people, students, interns, all of us, the pilots and everyone, are just so thrilled to be here to tell you about our project and get you inspired. As you all know, the world has many things that we can still look at, and the upper atmosphere is one of those. It's just, we'd love to have your support. If you want to go and learn more about our project, you can go to our website, www.perlanproject.org, and tell your friends. It's a great project. Thank you for your support.
That was so cool. Who has a question?
Yeah, you said you were flying down there. Are you flying the tow plane down?
Yes.
Okay. Do you take it back and forth?
Yeah, we've flown it back and forth now 3 times. It was 13,262 miles in a single seat.
And I noticed the glider was in low tow, and then it looked like.
So in terms of like data collected and the insights that you gather up there, what are the alternatives for these gliders that you create? Is it like near Earth orbit satellites? Are there any kind of other collection methods that we have?
I'll speak with the microphone. We do have potentially some soaring sondes. That's the next thing that we're looking at, to launch an autonomous vehicle into the upper levels of the stratosphere. Yeah. Soaring sondes. Uh-huh.
Thank you so much. It was a really, really good lecture, and congratulations on the 4 world records. So looking forward to see one more, obviously. And also, you guys are handing out El Calafate, which is an awesome, funky town. I loved it when I was down there. My question is coming from as a non-aviation expert perspective, because you mentioned that in the global south, there's not much of the flight or weather observation down there to observe the weather at this high altitude. So I was wondering, how does this method compare to a high altitude balloon in terms of reliability, cost, durability, and effectiveness on collecting those climate data?
Right. Like I said, with the Partners program, we do have a stratospheric balloon that is part of our project now. The cost for the Perlan Project, every year that we go down there, is probably close to, for the 3 months, 2.5 months that we're there, close to $800,000. So it is a costly effort to mobilize those people. With balloons, you are at the mercy of the wind, unfortunately. With the glider, we can stay on station for 6 hours or so until our oxygen, our batteries run out. And so we have more control. So I contend that both are important, but the glider is a more controlled environment. So you can answer the questions.
I was wondering if you could speak a little bit more towards the weather and wave component of this. So the first part is, do you send up weather balloons or get atmospheric data before you go, and how good does that data look? And then on the waves themselves, is there, in addition to, you know, sort of this updraft component that you can ride all the way, do the waves cast a shadow? Is there horizontal wind shear? And could you potentially exploit that in like a more dynamic soaring regime doing circles?
Okay, yeah, that's great questions. Okay, so the first one was about the weather balloons, and do we explore the atmosphere before we launch? Yes, we do. The problem with our balloon launches is that they're done at the El Calafate airport, which is downwind of the place that we really want to insert the glider in to get to the wave. It's probably about 20 to 30 kilometers east of where we'd like to be. So because of that, and it takes some time for the balloon to rise, by the time we get to the atmosphere height that we're interested in, we're downrange significantly, probably, 200 kilometers or so by the time we get to 50,000, 60,000 feet. We've successfully put the balloons up to 110,000 feet routinely. So it does give us a feeling. We can back calculate what the atmosphere looks like in those kind of settings. So it's not the best. My hope is when we go back again in 2025 that we will be able to put balloons on the Chilean side and launch them up over the Andes. So by the time they get over El Calafate, they'll be at the altitude that we want to see. The second part of your question was about the wave and how it actually is exploited. When we go to the wave, when the glider goes to the wave, Arnie's going and taking them and towing them out, and we're sniffing using some software and artificial intelligence now driven algorithms to try and understand where it is. But the true method and the true feeling for where we need to go is done through Arnie and the pilots in the Perlan.
Yeah, once we've got all of the modeling that they've done, give us, and the historical data, give us spots to go. But what we're doing is improving the models. And so when I get up, a lot of times, especially in marginal lift days, we'll throttle back when we get into like 42,000 feet or so, and I'll start towing the glider back and forth to these spots, and we'll look, the model says here, let's go over here, or let's go try over here. We didn't get it here, or we got it here, and boom, off they go. So that's just part of improving the models dynamically as we're going in real time.
Right, and so the waves set up in a primary wave, a secondary wave, a tertiary wave. And so we'll always insert them in the primary wave if we have the option to do so. And they'll stay there, and hopefully there's enough up air to keep lifting them. They need at least a 900 foot per second type of air uplift to just overcome the sink rate of the thin air at that altitude. So we have to be getting in some really good updraft type air from that mountain wave, the stratospheric mountain wave. If that doesn't pan out, we can drop back to the secondary or even the tertiary waves to try and take advantage of that. The spacing, the wavelength spacing between that is about 10 kilometers or so. So it's very tight, because the air is moving so fast, the pilots have to make a decision using the ground-based input from the third pilot flying down there, and all the meteorologists. We take a whole team of meteorologists with us as well to try and understand where we want to fly and just stay in that.
But when you get a record day, it's not a problem.
Yeah.
You get up there and you go, whoa, we got some lift today.
Yeah. On the record day that we set in 2018, when we did set the 76,000 record, we had to be very disciplined because we could have easily made it to 90,000 feet that day, we do believe. It was just amazing. The up air was just, wow, incredible. But we want to be safe. So every 5,000 feet, we have to go through that flutter test and all those different tests. And so by the time we'd gone through the test at 75,000, we were getting longer in the, not as much oxygen, not as much battery. We're always limited by the systems. So we wanted to wait for another day.
We've got a question back in the back row.
Hi, I wanted to say congratulations on all of y'all's work. I love the dedication to sustainability. And I was just wondering how climate change affects the Perlan Project in the long term. I mean, y'all have so much data. You've been around since 2006. I don't know, how does it look? Does it look good? Does it look, how does it look?
Yeah.
Well, it looks, from the last year, we thought, and Roberta's been an advocate of this, we need to go earlier in the season. And we think that we need to move at least a couple of weeks earlier, maybe even 3. Problematic is the climate. It's winter down there, and the further back we get, the colder and more miserable it is. But that could enhance our chances of getting higher. And is that a cyclical change or is it weather change? Well, they'll have to look at the data and try to. Hopefully, it'll help the modeling and help us understand it.
Yeah, my personal opinion is we are definitely seeing a climate change. It's getting warmer, definitely. We've talked to people in Antarctica, in the Argentine Navy and things, and they're seeing green grass growing where there was only ice. And we can see that in the glaciers there too. But atmospherically, we can see it. The polar night jet breaks down much quicker. It's not in place as much. And having that sudden stratospheric warming event, that was also a wake-up call. Yeah, I do think we're seeing something. And I am a climate change scientist, so I do have a vested interest in looking at that.
I neglected to say that in the intro. Dr. Roberta Vassadin is an atmospheric scientist. I think we have time for one more question, and I'll go to the back. Thank you.
When early in the presentation you mentioned that Einar was looking at New Zealand or
yes.
Argentina, and I'm curious now that you have this all set up here in Argentina and there's so few weather stations you mentioned in the southern hemisphere.
Yes.
Is there kind of a competitor team doing this out of New Zealand, or do you guys have sights on eventually moving over to New Zealand to collect different data?
New Zealand was a good first place to locate because there's so much more infrastructure there, but it is not far enough south latitudinally to get always predictably into that polar night jet atmospheric pattern. So that's why Einar and Steve Fawcett, they went there first, hoping that they could get that conventional glider in to the lift, but they couldn't. They had to come back out to El Calafate.
30,000 foot range. They didn't even come close.
They did it for like 3 years without effect, and then the next time they came, they went and they set that record.
Thank you. You teased us about Mars, possibility of flying
Yes, sir.
A robotic version perhaps on your project, on your airplane. But that makes me think about, is it there anybody who works on UAV equivalent of your machine that can do similar survey in a higher atmosphere?
Well, in the past, the Boeing had a very high altitude unmanned plane. There are unmanned planes that are in the works. There's always something coming along.
But nothing's gone quite that high and that predictably. That's what we're trying to do, is get some funding to be able to do that, actually.
And even the remote control, since we are in the upper
Absolutely,
Earth.
yeah. The autonomous, yes, that's the soaring sans that we were talking about earlier. So it would be something that could even be launched from, say, the egret and have folded wings that unfold and then go off, and we can fly it up into the wave. We can even make an extreme type of sans, so we could insert it into a thunderstorm or, the 70,000 foot problems and the tornadic thunderstorms and things. So we're looking at all those different kinds of things. We're trying to innovate in the aerodynamic and atmospheric type. Right, exactly.
I think that's a good point for us to call this. You'll have the opportunity to speak with them immediately after. I want to say in closing, just wow. I was so excited when I read about your project, and it's as someone who cares so much about the Explorers Club, what you are doing is really the very best of what our club aspires to. You have the commitment to path breaking, to kind of going to where no one has been before, but doing so with a scientific purpose, doing it as a team. I mean, the fact that you volunteered to come here tonight, we kind of operate on a shoestring around here. We are a nonprofit. They volunteered their time and travel to come here and speak tonight. It occurs to me that the two of you, you're really like the real life Top Gun there, because we've got the pilot, one of only 6, I believe, the egret's one of 6 in the world.
5.
5, okay.
And we have
22,000 hours, is that right, Arnie?
25.
25,000? And then Dr. Roberto as the scientist behind it. Just wow. As a token of gratitude, hopefully, I noticed you got some Velcro on some of your spots. We've got 2 Explorers Club flags. These are actually from the club's Military and Veterans Initiative, but I think it would work well with what the two of you are doing. And I just want to say thank you, Roberto and Arnie. You'll have the opportunity to meet them individually. The bar is open. Next Monday, we will be having a talk on, I want to make sure I get the name right on this, New York Times bestselling author Hampton Sides will be lecturing on his forthcoming book, The Worldwide Sea, The Final Voyage of Captain James Cook. So please keep coming back, and thank you for coming tonight.
Yes, thank you.
That was awesome.
Cool. Good. I'm glad you liked it.